Hi there, my name is Tim Cruse. I lead the ASEAN prototyping team here at Amazon Web Services, and I'm so glad to have you joining us today for this online summit ASEAN recap. I also hope you are all safe in these challenging times. With my team, within the prototyping program, we help customers contextualize complex uses of the AWS platform by building working prototypes of specific use cases in their environments. In a nutshell, we help bring your awesome business ideas and challenges to life. If you need help on your next big project, you should ask your local AWS team to tell you about how we can help. Now, the reason I bring up prototyping is for this particular session. Recently, we've been doing a lot of projects with customers around computer vision, and mostly around scalability of these edge vision workloads. Customers come to us constantly challenged by how they are going to scale their project from that 1 or 2 cameras on their desk to the thousands, if not millions. This is why I thought I'd focus this session to give you a quick rundown of how we work on these types of projects and the types of architectures we implement. Let's dive in. For this session, let's start with a bit of context. Why is this scaling such a problem? Then we'll talk about planning and tools and architectures to implement to facilitate the development process. Then I'll touch upon zero-touch deployments at scale. And finally, we'll look at one common architecture pattern we've been implementing for customers wanting to leverage computer vision for quality assurance. Ready? Why is this scaling problem such an issue? Well, most of the customers I've talked to about edge vision and machine learning are scratching their heads on how to efficiently solve their deployments of their models securely and at scale. Machine learning and AI is the new buzzword. We can now solve anything and everything with machine learning. At least that's the word on the street. I tend to disagree, but that's besides the point. Access to machine learning has been democratized, and it's becoming easier and easier to develop and train your own machine learning models. Put that into a Raspberry Pi, add a USB camera, and suddenly you're getting notified every time the cat hops from that chair to that chair. AWS provides extensive tooling to allow training of machine learning models and deploying them on your edge devices. With SageMaker, for example, Olivier last year showed everyone in the room how he had trained his camera to look for a floating unicorn in the crowd or some guy wearing a hot dog outfit. Besides these fun demos, we provide our developers with an actual edge camera device, the AWS Deep Lens. It's an actual camera with computing capabilities, which is able to run machine learning models on the device itself, so you can analyze the video frames in real time at the edge without having to go to cloud. Customers and users around the world have been leveraging these tools to create really great solutions. I've worked with customers using these tools for safety. Cameras can now detect whether the personnel is wearing their proper safety equipment, or only opening doors when the right personnel is identified. Some customers use machine learning for monitoring their machines. Instead of placing more sensors on their old machinery, why not point a camera on the different dials, LEDs, and screens, and convert all of that into data that gets live streamed to cloud via the AWS IoT services? Great use cases where you are very limited by what you can change on your equipment. I love this use case. Who has not heard of Fender? The world's most amazing guitarists all probably own one or more Fender guitars in their collections. For those that don't know, Fender is an American guitar manufacturing company. They design and manufacture electric and acoustic guitars as well as a lot of guitar-related products. Their guitars are built with amazing craftsmanship and woodworking. What Fender told us and we discovered is that a guitar is in fact an aggregate of multiple sections of wood. It isn't one big piece of wood that gets cut into the shape of a guitar. It's actually multiple, 3 or more slabs of wood that are glued together and then cut into the shape of the guitar. And that's where machine learning and edge vision comes into the picture. Wood has its own particularities, its own colors, shapes, and grain. One long tile of wood, if you cut it into 2 pieces, won't both have the same exact color, grain, or designs. And in order to create beautiful looking instruments, it actually helps if you can match those 3 or more slices of wood to match as much as possible. Using edge cameras and machine learning in their production factories, Fender is now matching their guitar wood to make sure they match as much as possible. Not only does this reduce the time it takes to find the matching pieces, increasing their productivity, it also allows them to increase their quality. Such a great use case, and Fender actually started out leveraging deep lens for this, which they placed in their manufacturing lines. Deep lens is a great tool and really shows how easy machine learning has become for generic use cases. The AWS Deep Lens service has pre-built models you can simply deploy on the device itself for multiple use cases. Detecting objects, playing around with the images to create artistic styles, detecting faces, or the ever infamous hot dog recognition algorithms. And this is where the fun at the tip of the iceberg wears off. Suddenly, whilst I've created the best COVID machine learning model that allows me to detect if someone is not wearing their mask in the vicinity, I'm stuck. I can't remember what I had to install and the steps to get it working on my camera. Or it's all great and works on my desk because I SSH'd into the device, installed the tools, uploaded the machine learning model, but now I need to set this up for 1,000 cameras we have in the building. And if this project works, I'll need to roll this out across all of our offices. This is exactly where a lot of customers get stuck. The great project we were working on, which is showing a lot of promise on our desks, has become very complicated in figuring out how we're going to deploy this at scale, without spending an hour or more per camera. So, this is why, having gone through this challenge many times with our customers, I thought this session could help and provide some guidance on how to help you accelerate your development and deployments. When talking about edge vision workloads, we generally advise to take into account these 3 main considerations. Plan for the real environment. What we mean is that the real environments where the camera will be installed will be 1,000,000 times different to that very stable and controlled environment in your lab or on your office desk. Every site will be different. The lighting, the ambient visual noise, the angles, the type of objects, the reflections. So many different reasons your model won't behave as well in the real environment. So you'll need to retrain to take into account those differences. But will you want to train your desk images or real environment images? And how are you going to simplify getting those images knowing that the camera will be installed on top of a pole in that very dangerous area of the plant? Are you going to go on site and take pictures with your iPhone? Your phone's camera will be different from the edge camera you are planning on deploying on site. One of the most forgotten elements is lead times. Sometimes these edge industrial cameras can take weeks to get to you in the numbers you need. Suddenly, whilst everything is ready to go, you have to wait a couple weeks. Sometimes these industrial devices are not the kind of device you can go find off the shelf at the local electronics store or Amazon.com. Planning is key. Plan for the real environment ahead of time. Plan for the real device. Train from the real device images. Then we need to consider deployments at scale. Whilst there's the actual deployment of the physical device, there's also the deployment of the actual software, dependencies, updates you need to install on those devices. You can't keep SSHing into every single device one at a time and install the tools, run some tests, and move to the next device. And you shouldn't allow for SSHing into the device in the first place. But suddenly, how do I install what I need on the device if I can't SSH into the device anymore? You need to minimize the on-site work. Aim for that zero-touch deployment. Finally, you need to consider operations and security. You need to manage, maintain, and update your applications, your containers. And how do you update to the latest OS level security patch when you need to do this for 10,000 cameras spread out across the world? Your business logic or your models also need to be updated over time. And this is where suddenly this machine learning problem has now become an IoT problem to solve. For this, we have developed multiple IoT services, of which I'll highlight 2 specific ones for the edge vision-based workloads. The first one, AWS IoT Greengrass. Greengrass is software that we provide for no fee, runs on Linux, and allows for managing and orchestrating your IoT use cases at the edge. I do recommend you sit on other specific and dedicated sessions on Greengrass because it is extremely useful for edge IoT workloads, not just edge vision capabilities. But of its many features and capabilities, I wanted to highlight the following for edge vision use cases. Greengrass supports machine learning inference. What this means is that you can train your models in the cloud with SageMaker, for example, and then deploy those models onto your device with Greengrass and infer off of the data, in our case, images. And Greengrass supports access to local hardware capabilities of the device, giving you machine learning models access to the GPUs, for example, to accelerate the inference. Greengrass has connectors, which are pre-packaged capabilities you can use to connect Greengrass to external services, simplifying the onboarding and section of your edge device capabilities without having to code all of it yourself. You can synchronize and deploy secrets to the device. If suddenly your device needs to connect to a local database, for example, you don't want to have to hard code your credentials, and you want to be able to rotate those credentials and manage that from the cloud. Greengrass supports and orchestrates containers on your device, extremely valuable feature. A lot of customers have packaged their business logic into containers and are simply deploying those onto their devices via Greengrass. Finally, the Stream Manager, which allows your business logic to collect, process, and export high volume of data streams from the edge device to Kinesis streams, for example. These core capabilities within Greengrass will be used in the architectures I'll be showing you to manage your edge vision workloads. Another critical piece of the puzzle is AWS IoT Core. IoT Core is a managed IoT messaging broker. Greengrass connects to IoT Core securely and uses it for triggering deployments, sending and receiving IoT messages. For example, the inference that is made at the edge can get sent to cloud via IoT Core, and your business applications can access this data directly. IoT Core is an identity service that allows you to manage and authorize your devices to connect to the cloud and provision unique identities. Effectively, every one of your Vision Edge devices will require unique certificate to authenticate to IoT Core. It's a fully managed device gateway optimized for IoT workloads. This means the service will scale to enormous proportions to support 1 to millions of devices, if not billions, that you may have. It's a reliable and fast connection message broker, allowing for publishing and subscribing of messages to and from your devices and to cloud. The broker supports multiple protocols, of which MQTT, HTTPS, and WebSockets. Greengrass will connect to IoT Core over MQTT and leverage the same level of security as any IoT device requiring a unique certificate. The rules engine is how you pass your data from the broker to the different applications consuming it. You can query the data in real time as it's passing through the broker and choose to pass it on to multiple different AWS services, allowing you to store data into databases, pass it to microservices, archive the data, or leverage analytics services for further processing. Finally, the device shadow allows to manage the state of your devices, allowing your applications to interact with the device even when the device is offline. In a nutshell, IoT Core will be the data communication and ingestion service for your edge cameras, as well as allowing for command and control. Now that we've addressed the foundational IoT services used in such architectures, we can discuss a couple key architectures, even in their simplest form, that allow to plan for your machine learning development in real environments. The following very simple architecture illustrates how you would leverage Greengrass in your device in the real environment. On top of that pole in the production line or in dangerous environment. You would configure Greengrass to run one simple Lambda function. That function would be responsible for taking pictures. Here we're taking pictures of items on conveyor belts, for example, because we have a quality assurance use case. But we could be taking pictures of the street or our dangerous environment. That Lambda function will trigger capturing those images and sending them to S3 for storage, and starting the machine learning training. As the set of images arrives, we now need to organize and classify or define what we're looking for. Amazon's SageMaker Ground Truth is a fantastic tool allowing you to leverage your teams or outsource that activity to third parties for a fee. If you are classifying, you can create image classifying jobs, or if you are in need of creating bounding boxes, you can create those too. The idea being that you then send your images to a user base for them to provide you with that interpretation of those images. Is that image a cat or is it a dog? Or here's the bounding box to the cardboard box on the conveyor belt. That image set will then be used to train your model. For training, we will use Amazon SageMaker, a fully managed training and model hosting service. SageMaker has two built-in main functions. The first one allowing you to host your notebook instances to create your training workflow. This will trigger training jobs that will scale and allow you to train models in minutes where before training could take days on your own machine. The second main function is for hosting your trained models. This allows your cloud application to infer from the hosted models and scale accordingly. This feature we won't be interested in too much about because we actually want to infer on the device itself. But this is where Greengrass integrates with SageMaker as well as S3. What this means is that you can deploy your SageMaker hosted models directly onto your device leveraging Greengrass's ML inference capability. Or you can choose to store your trained model on S3, and Greengrass will leverage that model for its deployments. SageMaker combined with SageMaker Ground Truth provides a great workbench of model training and hosting for your applications. But in our scenario, we want to discuss edge, only the edge. And with the edge comes the limited scalability of the hardware resources of our device and the inherent hardware capabilities of our devices. You may have chosen a specific industrial hardware that has a specific GPU capability or specific chip to accelerate machine learning algorithms. This is extremely powerful as, for example, offloading these heavy calculations to GPUs will help accelerate your ability to infer from the images and video feeds in real time. The NVIDIA Jetson platform has multiple versions from the Nano to the TX2 to the Xavier, where as you go up in performance, you can expect to be able to analyze more video feeds per device and at higher frame rates. In order to optimize your SageMaker trained model for your hardware, we've developed the SageMaker Neo runtime. SageMaker Neo takes your MXNet, TensorFlow, or PyTorch trained models and re-optimizes them for speed and size in order to match your dedicated hardware, supporting Intel, NVIDIA, Qualcomm, Cadence, ARM, and Xilinx optimizations. This is very powerful because when dealing with the edge, first of all, deploying a very complicated model implies deploying a large model memory-wise. Neo will reduce the footprint of your model. Second, by leveraging SageMaker Neo, you can simply compile your model to leverage your device's hardware acceleration capabilities without having to worry about the complex custom hardware libraries and SDKs required to leverage those specificities. Your models will gain on speed of execution at the edge. From a high level, these tools help optimize and plan your model training for the edge. Now, let's start talking about what I've called zero-touch deployments at scale, or the lightest touch, or better, trying to minimize the amount of manual work required per device. Ideally, you want to produce your edge devices with no manual step whatsoever. Depending on your application, you will still require some. How can we minimize the amount of manual steps and leverage the cloud to manage that for us? For this, we leverage three tools, first of which will be the installation of some custom onboarding app of your making. Could even be a small script. The purpose of that app or script is to set up the very bare minimum on the device. Could be to configure an endpoint, for example. In some scenarios, you actually don't even need such apps. Your edge devices may have unique hardware capabilities like hardware secure elements that allow the device to generate its own keys securely and tamper-proof. Typically, in those cases, you may not need this type of onboarding app because your device has those customizations built into the hardware upon manufacturing at the factory. The main tool will be the AWS Systems Manager, and the second one being Ansible. The reason we leverage Ansible is because it's almost become an industry standard for easy setup of applications and dependencies on servers by running different playbooks. A Linux Edge gateway or camera is no different to a cloud Linux server, but the main component here is the AWS Systems Manager or SSM. SSM is a great tool allowing you to manage the device at the OS layer. It's an agent you install on the device. That agent registers itself to the cloud SSM service. From there, you can then trigger running Ansible playbooks and track their execution, or you can simply trigger the execution of scripts. This is how we will install the base dependencies and applications on the device based on specific applications level versioning. Once your device comes online, effectively, the device will register itself to SSM and then run installation scripts to install Greengrass and all the machine learning dependencies, if they aren't already present on your device. Generally, what we recommend customers to do is create a base image for these devices that have these two tools installed, nothing more. No need to package up and think about all the different dependencies your application will require. Managing the onboarding of your devices from the cloud simplifies the whole process. Okay, now I've ran through very quickly some of the basic AWS services that we can leverage to support scaling out our vision-based edge workloads. Let's dive into the real use case. In this use case, we will be looking at the necessary steps and architecture to support a scalable quality assurance use case in manufacturing environments. What does that mean? Well, let's say you produce shampoo, for example. Well, your production lines will have different stages within the process where you may actually produce the plastic bottle. How do you make sure that your bottles are produced to spec? That no bending or decoloring or missing or weird plastic forming is produced? Or you could simply be sticking a branding sticker on the bottle, and you may need to check that the sticker is not only placed correctly on the bottle, but that the printing is correct or the sticker is not upside down. All these defects can arise in manufacturing environments for thousands of different reasons. The plastic quality supplied isn't exactly to spec on that day, or the temperature of the machine was just 1 degree under the norm, or Bob the mechanic dropped his wrench or forgot to tighten some screw. Whatever the case, defects will arise. And to improve the efficiency of your operations, the goal is to reduce those defects. And this is where cameras can come in handy. Instead of a manual and visual inspection of the line, why not leverage a camera to do that? The camera looks at your products, connects to AWS, is managed by the different services we discussed, and we can determine if the products we are looking at are good or bad, and we can take action in real time. So what does this look like from an architecture point of view? From a high level, our camera or gateway infers off of the video feed and sends the data to cloud. Easy. Our architecture is thus split into different services and capabilities. At the edge, the inference and deployment of capabilities. We'll have our provisioning and onboarding APIs for our new devices. In the center, we'll have the command and control and ingestion of IoT data via IoT Core, which will pass that to our visualization services. That could consist of web applications where your users authenticate to via Cognito. The storage layer, leveraging S3, opens up to data analytics pipelines, allowing you to further process all this data to thus come back with, for example, those correlations on machine temperature and the defects. This is only made possible by not only simply deploying a good product, bad product model, but on the acquisition of data from those models and being able to correlate that information with other IoT data from your machines and environments. The purpose of this presentation is to focus on the scalability and provisioning. This is inherently how our provisioning architecture would look like. In the center, our SSM agent that will work with the SSM service in the cloud, triggering and integrating with either the onboarding app, should you need to onboard your devices with their specific metadata into your backend databases and applications. You do need to have some registry and management of your device with elements of metadata you may want to keep track of, as well as the device certificates. Whilst IoT Core supports all these capabilities, device onboarding generally requires custom data stores based on your use case. SSM triggers Ansible playbooks that will inherently install Greengrass and supporting dependencies on the device. From there, the device is ready to go and your business logic is ready to be deployed onto the device via Greengrass. For this, you'll generally implement your own UI tooling, allowing you to have visibility on the state of these deployments and your own custom device APIs. Summarizing it, your edge device has the bare minimum applications installed, SSM agent, Ansible, and your custom onboarding app. That's all. Remotely, with the device management and SSM capabilities, you can now remotely install the different dependencies on your device, whether it's a specific version of the Greengrass core software or the AWS CLI to interact with different AWS services, installing Docker so that Greengrass can orchestrate and deploy your containers on the edge device. Your Lambda functions will either be in Node or Python. You'll need to install those on the device, but also potential libraries like OpenCV in the specific versions of your application's needs. All of this triggered and managed by SSM and Ansible. Not for one device, but for all the devices. Suddenly, you're not operating with one device on your desk anymore. You are onboarding tens or hundreds or thousands of edge devices and managing their life cycles and application deployment. Another element we discuss with our customers is the importance to abstract the different layers on your devices. This is extremely important as you scale and suddenly you have to manage different hardware types with different business logics and functions. For this, I like to think of it like this. You'll have device types, device images, and device blueprints. The device image is probably the easiest. It'll be your base OS, Ubuntu, CentOS, Debian, etc. Obviously, some hardware devices may not be compatible with this Linux distribution. This is something you'll have to manage and capture as you deploy. Then we talk about device types. A Raspberry Pi or an Intel UP board are two device types, despite them both being able to run Linux. Obviously, they will both have their inherent hardware capabilities, CPU, RAM, flash, but more importantly, they are peripherals, with GPU, without GPU, etc. But a Raspberry Pi with a camera attached is just a Raspberry Pi with a camera attached. It's the device blueprint that suddenly gives our device a purpose. If the device blueprint has business logic and machine learning capabilities for detecting faces in video feeds, for example, well, if you deploy that onto your Raspberry Pi with a camera, then your Raspberry Pi with a camera isn't just a Raspberry Pi with a camera anymore. It's a face-detecting camera. The device blueprint gives purpose to your device. This is an abstraction I advise customers to think about as they build their business logic. Your hardware may change over time, or you may need to manage multiple types of hardware or devices, but leverage the same inherent capabilities. Suddenly, if you build the necessary tooling, you could in theory deploy face-detecting cameras independently to deploying Raspberry Pis or Intel UP boards. This architecture illustrates this concept and how we've implemented this via prototyping engagement for a couple customers. The main idea behind this being to create an application to manage your device types and your device blueprints. Inherently, you still need to manage your own machine learning training, etc. But the idea being to create an application and UI allowing you to manage that complexity for you via specific tooling. Once all of this is in place, the tooling packages up all the blueprints and inherent specificities of your device types to simplify the deployments on your fleet of devices, resulting in your devices running your business logic in, say, a container orchestrated by Greengrass to become a face-detecting camera at the edge. The key concepts revolving around device setup via the device types and blueprint, and a deployment service responsible for compiling the different assets and leveraging Greengrass deployments to deploy on the device itself. Finally, in order to further help our customers, we've open sourced one such application on our GitHub repository. The AWS IoT Kickstart demonstrates how you would go about creating these device types and blueprints, and with a built-in deployment service, deploys those capabilities on your devices. A great way to see how this could be done and potentially leverage for your POCs and getting started. The tool also has live visualization capabilities, allowing for simple data visualization from your device. And this is where we start talking about data. What is the purpose of a face-detecting camera or a good product, bad product camera if we don't have access to the data and act on it? This illustrates our quality assurance data use case. We use the Stream Manager on Greengrass on the device to ingest the results from an inference from the video feed. We could even have multiple cameras connected to our gateway at multiple stages of the production line, for example. We may choose to persist some of that on local storage or on-premises database, but the Stream Manager will then stream the data, the actual results of the inference, to Kinesis, where that will trigger different data analytics jobs. And effectively, this is where we can start deriving automated and amazing business value. Which brings me to the last IoT service that we use to help improve our customers' efficiency, AWS IoT Sitewise. Our edge camera detecting defects on the production line now becomes a simple sensor on the production line. Just a simple sensor detecting good or bad. Similar to the temperature sensor feeding us data about the current temperature. AWS IoT Sitewise is an IoT service that allows industrial customers to connect their industrial equipment and leverage different industrial protocols to extract data, model your assets and equipments in the cloud. You can process the incoming data to transform it, and inherently you can then derive metrics. And in the context of our use case, what we were interested in was OEE. We can now monitor the overall equipment efficiency of our manufacturing line, all the way up to the plant level, which is running multiple production lines. OEE is calculated by the multiplication of availability, performance, and quality. Availability, how much time has my equipment been running? Performance, how fast is my equipment running? Quality, how good are the products I'm producing? And it's on this quality value that our newly created sensor can feed into. We can now create site-wise monitoring dashboards that give business stakeholders live visualization as to the efficiency of our equipment. Combined with the data analytics and storage of data in the cloud, we can then try to understand why Plant A is operating better than Plant B. Maybe there's a difference in suppliers between those two plants. Maybe the teams are operating the equipment differently. Who knows? But acquiring all this data allows us to find out. On that note, I hope you found this session useful and hope that I managed to convey the benefits of leveraging AWS and the different tools available to help you scale your Edge Vision workloads. I do hope that you are all staying safe and hope to see you again real soon at our different events. Do have a look at our training website where you'll be able to take part and schedule training classes for yourself or your teams. Increase your skills on cloud services and validate those skills by getting AWS certified. I want to thank you again for attending our AWS Online Summit ASEAN recap, and please don't forget to fill in those surveys. Have a great day.